Hello, students. In this video, I'm going to work the final exam from fall 2023 for Math 1341, Calculus 1. Specifically, though, the sections of Calculus 1 that are restricted to biology-related majors. So in particular, we will see some differential equations on the final exam. Now, if you look at the length of this video and you realize students have 2 hours to take the test, understand our actual test might be slightly longer. Some of the questions could be, at least to a student's perception, slightly more involved. It just depends on the semester. This video is a wonderful review of the concepts of the semester, but it shouldn't be your only review. In particular, inside the Canvas course, I have links to so many other review pages. Okay, so now let's get into working the fall 2023 final exam. All right, number 1. Well, we have a picture and we have a question on limits and continuity. So first of all, we are addressing the function at 1, which is here. We want to limit from the left, right, overall limit, and function value. Okay, the limit from the left is y equals 3. The limit from the right, y equals 0, this means the overall limit does not exist. So limit from the left is here, limit from the right is here. Function value, this is where it's filled in. F of 1 equals 0. And then finally, f of 4, well, here f of 4 is 2. You notice the limit as x approaches 4 of f of x is minus 1, but f of 4 is 2. Now, list all x values where the function is not continuous. From a picture, we think about where do we have to pick up our pen. So the function is not continuous at 0, at 1, and at 4. Next, we have 2 questions on limits. Evaluate each limit or show it does not exist. So this first one is a limit at 6. Thinking about what's happening here, we have 36 minus 36 over 30 minus 30. This does not say the limit does not exist. This is an indeterminate form that tells us we need to do algebra, do some more work here. So we can factor the numerator and also the denominator. The numerator, we get x minus 6 times x plus 6. The denominator, we have 5 times x minus 6. We can cancel off the x minus 6 over x minus 6. So we have a limit as x approaches 6 of x plus 6 over 5. What's left? This is continuous at 6, so we can evaluate. We get 12 over 5. So my answer is 12 over 5. Next one. Okay, we have a limit at infinity. Because of this square root, I'm going to do this in 2 steps. So first, let's look what's underneath the square root. We have 8 plus 5x squared divided by 9x squared minus 3x. Just to get this limit, we would divide every single term by x to the highest power that we see. In this case, it's x squared. So, oh, I got my equal sign. We have a limit as x approaches infinity. We would have 8 over x squared plus 5 divided by 9 minus 3 over x. Okay, I divided both the numerator and denominator by x squared. In a sense, I have just multiplied my fraction by 1. Now, we use properties of limits. So this one and this one both go to 0. So I get 5 over 9. Now, I'm not finished here. What's left, okay, this is my second, which I'll do in blue. Second, Well, the square root is a continuous function, and so we may bring the limit inside the square root. What this amounts to is we have a square root of 5 divided by 9, which we can write as the square root of 5 over 3. Very nice. Next page, we have average rate of change and definition of derivative. Well, my function is square root 5 plus 4x. We want the average rate of change between x equals 1 and x equals 5. Okay, this is f of 5 minus f of 1 divided by 5 minus 1. What I frequently will do is come to the side, calculate f of 5. This would be the square root of 25, which is 5. Come to the side, calculate f of 1. This would be the square root of 9, which is 3. Now I can jump back in. So I have 5 minus 3 over 5 minus 1, which is 4. You see, we get 2 over 4. Typically, we want to leave this kind of answer as a simplified fraction. So my answer is 1/2. Okay. Letter B, we want the derivative at x equals 1 using the limit definition of derivative. If we just use rules here, we would not have any credit for letter B. So what I want to do is start with the numerator, f of 1 plus h minus f of 1. Well, my function, let me move this up so we can see it again, is the square root 5 plus 4x. Okay, first, evaluate at 1 plus h. We have 5 plus 4, 1 plus h. Then evaluate at 1. In a way, you see we've already evaluated at 1. We get 3. So minus 3. Okay. This first term, we have a 4 plus 5. So I have 9 plus 4h minus 3. Now there's really two different kinds of strategies that we practiced in these questions. When we have something like this, we want to multiply by this conjugate here. But of course, multiplying by just square root 9 plus 4h plus 3 would change the expression. And so I have really just multiplied by 1. But what's going to happen here? Well, my numerator is what's going to be wonderful. So the denominator, I'll just copy, and paste. My numerator, well, when you have the first, we get 9 plus 4h. Let's write it. The last, we get minus 9. But then the reason why we're doing this is the inner term and the outer term add to 0. And so we're left with 4h divided by square root 9 plus 4h plus 3. Well, this is h times something, which is what we want because the next step is we divide by h. In fact, maybe I'm ready to calculate f prime of 1. This will be a limit as h approaches 0. Well, take this, which is our numerator, f of 1 plus h minus f of 1, and we divide by h. But when we divide by h, well, that's what we get. The beautiful thing is, this is now defined at h equals 0, and so we may evaluate. What do we get? We get 4 over 3 plus 3. 4 over 6, or 2 divided by 3. Now, we want an equation of the tangent line at x equals 1. Well, we just calculated our slope, 2 over 3. The point will be 1 comma 3. That's the point that's on my graph and also on the tangent line. So my equation, y minus 3, is the slope, x minus 1. Very nice. Number 4, we have 3 derivatives. Differentiate each function, and we do not need to simplify our derivatives. Well, this first one, you see I have one function times another function. So when I go to differentiate f, this will be product rule. Okay, here we go. We have first, which is x to the 7/2 times. Well, if I want to differentiate natural log of 1 minus x squared, this is a chain rule. So we have derivative of the outside evaluated at the inside times the derivative of the inside function. So far I have first derivative of the second, then I put a plus, we have second, and then times the derivative of the first, 7/2, x to the 5/2. Here's f prime of x. Next one, let's differentiate g. Maybe the thing to observe here before we get started, we have this 6th root of x to the 5th. We need to think about what power is this. Well, this is the 5/6 power, so x to the 5/6. Now I'm ready to jump into my derivative of g. We have one function divided by another. This will be the quotient rule. Okay, so we have denominator 4 ln x plus 3 times the derivative of the numerator, which is 5/6 x to the minus 1/6 minus the numerator, which you can either write as a power or you can write it as the 6th root of x to the 5th times we have derivative of the denominator, which is 4/x, and then all over denominator squared. This was the quotient rule. Okay, here's g prime of x, and I did not simplify. Next one, we have h of x. Oh, well, first thing, I have this one inside function right here. So I see, fundamentally, I see an outside function and an inside function. Let's do the chain rule, h prime of x. So when we differentiate the sign, we have the cosine. Okay, put in the entire inside function, which is e to the x plus x cubed times the derivative of the inside function. Well, to differentiate e to the x plus x cubed, this is chain rule. So we have 3 squared, put in the entire inside function, finally times the derivative of e to the x plus x, which is e to the x plus 1. So this example, we had sort of a nested chain rule. We had to do the chain rule 2 times. Number 5, implicit differentiation. Very nice. How do we do these questions? Well, we differentiate both the left-hand side and the right-hand side of the equation, understanding that every time we differentiate a y, we multiply by dy dx. Comes from the chain rule. First, we differentiate the cosine. So we have minus sine x. Differentiate minus y squared, we have minus 2y dy dx. And this will equal, well, here we have a product rule, 3x times y to the 4th. So we have first times the derivative of the second, which is 4y cubed dy dx. And then plus the second times the derivative of the first. So I've differentiated both the left-hand side and the right-hand side. The next step, we want to move everything with dy dx to one side of the equation and everything without dy dx to the other. Okay, so maybe I will move all my dy dx's on the right-hand side. So I will have minus sine x minus 3y to the fourth. This will equal, well, when I multiply these two coefficients, I get 12. So I have 12xy cubed, and then plus 2y, all times dy dx. My last step is to divide both sides of the equation by this, which will allow me to solve for dy dx. Okay, so dy dx equals, we have minus sine x minus 3y to the fourth divided by 12xy cubed plus 2y. Very nice. Number 6, f of x is x to the fifth minus 2x to the fourth, and then I have multiple questions for you. First, we want to find the x-coordinates of all critical points. These are called critical numbers. Okay, so take the derivative. What can I factor out of every single term here? Well, an x cubed. So I have x cubed times 5x minus 8. So my derivative is 0 when, well, either x is 0 or this part would be 0, which says x is 8 divided by 5. Okay, next part, we want intervals of increasing, decreasing. So we divide the domain. The domain of this function is minus infinity to infinity. Well, we divide the domain into open intervals based on our critical numbers. And I can write the open intervals underneath. This will go minus infinity to 0. The next one, 0 to 8 over 5. The next one, 8 over 5 to infinity. Okay, then we make a little chart. What we need to do for intervals of increasing and decreasing is test the sign of the derivative. We know a function is increasing on open intervals where the derivative is positive, and the function is decreasing on open intervals where the derivative is negative. Now, we can pick anything. Say minus 1. We could pick 1, which is between 0 and 8/5. And then I could pick 2, which is bigger than 8/5. So we will test minus 1, 1, and 2. We're interested in the sign here. So x cubed is negative, positive, positive. 5x minus 8 is negative, negative, positive. 2 negatives gives us a plus. 1 negative gives us a minus. So I can put these underneath. It goes plus, minus, plus. Now my function is increasing everywhere I see a plus, which is minus infinity to 0 and 8 over 5 to infinity. My function is decreasing everywhere I see a minus, 0 to 8 over 5. Next part, we want to specify the x-coordinates in which the function has a local max and local min. Okay, so let's test our critical numbers. We have 0, we have 8 over 5. Now I typically just recopy. So around 0, we have plus, minus. Around 8 over 5, we have minus, plus. Now we sketch. This says increasing, decreasing. This says decreasing, increasing. Okay, you can see we have a local max at x equals 0. You can see we have a local min at x equals 8 over 5. We've used our intervals of increasing, decreasing here. Okay, next part, we want concavity. So my first derivative, maybe I'll just copy and paste this. All right, there's my first derivative. What I really need to use in D is the second derivative. So we have 20 x cubed minus 24 x squared. Factor out what's common to both terms. We can factor out 4x squared. We're left with 5x minus 6. So my second derivative is 0 at x equals 0 and 6 over 5. Once again, we divide the domain into open intervals, but this time I'm going to be working with the second derivative. So here this goes minus infinity to 0. We have 0 to 6 over 5. We have 6 over 5 to infinity. Let's see. I need to test the second derivative. Maybe I will just do this smaller underneath. So here I can test the second derivative at, say, minus 1. What do I get? Well, you notice this part is positive. And then here, this part at minus 1 would be negative. So this is negative. It should be clear when you're working with these what you are testing. So here you notice I indicate that I am testing the second derivative. Okay, great. Next one, let's test at 1. Okay, this part is positive, while 5 minus 6 is negative. So the second derivative at 1 is negative. And let's test at 2. This part, always positive, but here at 2 would be 10 minus 6, which is positive. So the second derivative at 2 is positive. Okay, so underneath goes minus, minus, plus. Okay, so my intervals concave down everywhere we see a minus. Maybe I'll do that first. This goes minus infinity to 0 and 0 to 6 over 5. Concave up everywhere we see a plus, 6 over 5 to infinity. Now, the x-coordinates of inflection points 0 does not correspond to an inflection point because we do not switch concavity. But here at 6 over 5, we do have an inflection point. So that is my answer here. Number 7, hooray, differential equations. Which of the following are solutions to the second order differential equation? Well, we're going to have to check. It might be none of them, 1, 2, or all of them. The only way we know is by checking. So let's start with letter I. Y prime is 5e to the x. Y double prime is 5e to the x. Okay, that was kind of fast, but now let's jump into our differential equation. Y double prime plus 3y prime minus 4y. This equals 5e to the x plus 3 times 5e to the x minus 4 times 5e to the x. Okay, what do we have here? I have 5 plus 15 minus 20 times e to the x. Oh, okay, this will be 0. So let's circle it. My circle, well, became a box thanks to GoodNotes, but I will leave it like that. Next one, you notice we have a minus 4x up inside the exponent of e. This is chain rule. So every time I differentiate, I am multiplying by negative 4, which is the derivative of the inside function. Therefore, y prime is minus 4e to the minus 4x. Y double prime, this will be 16e to the minus 4x. Very nice. Now let's jump into my differential equation. y double prime plus 3y prime minus 4y. Okay, we have 16e to the minus 4x plus 3 times minus 4e to the minus 4x minus 4e to the minus 4x. Let's think about the coefficient here. We have 16 minus 12 minus 4. 16 minus 12 minus 4 is 0 times e to the minus 4x. So we get 0. Hooray! Okay, we have another solution. Let's circle it. Letter 3. Y is x plus e to the x. So the first derivative is 1 plus e to the x. And then my second derivative is e to the x. Okay, let's jump into my differential equation. Y double prime plus 3y prime minus 4y. This equals y double prime is e to the x plus 3. Here's y prime. And then minus 4y. What do we have here? Well, we have e to the x minus 3. Uh-oh. This should be a plus. Very nice. Now let's see what we have. We have e to the x plus 3 e to the x minus 4 e to the x. Okay, those terms add to 0, but then we have 3 minus 4x. This is not equal to 0. So we do not circle letter 3. This will not be a solution. Number 8, medication enters the bloodstream through an IV at a rate of 7 milligrams per hour. The body eliminates 25% of the medication present in the bloodstream per hour. Let's set up a differential equation for y of t. Okay, the rate of change of y is 7 minus 0.25 times the amount present at that time. So here we go. It's autonomous. Y prime is 7 minus 0.25y. What is the equilibrium solution to this differential equation? Well, we set this capital F of y, which is this function over here, to 0 and solve. So we get 0.25y is 7. Y would be, well, it's going to be 7. Really, this is divided by a fourth, or 7 times 4, which is 28 milligrams. More autonomous differential equations. Here we want to find all equilibrium points, determine their stability, and then we have a second part to this question. Very nice. Well, we want to set this to 0 and solve. Well, first I need to factor because it is a quadratic. So this will give us our equilibrium points. This factors into minus 3 plus 4. Let's check. Multiply. We get negative 12, and then we add, we get the positive 1. Very nice. So my equilibrium points are y equals 3 and negative 4. Now I'm going to draw a little picture. Here's negative 4. Here's 3. Okay, well, we could have 0 here. We could have minus 5 here. And then we can have 4 here. And this is very similar to things we did a few pages ago with intervals of increasing, decreasing. It's just that my derivative is a function of y. Okay, great. So at 4, stare at this, which is the derivative. We have positive, positive. My derivative is positive. At 0, we have negative, positive. My derivative is negative. At minus 5, negative, 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 negative. My derivative is positive. Okay, so here my solutions are increasing, here decreasing, and here increasing. Now we just look at the picture and we can write our answer. We notice that y equals 3, unstable. Y equals negative 4, stable. Suppose y of x is a particular solution with y of 0 is 1, so it starts somewhere in here. What is the limit as x goes to infinity, y of x? Well, the answer is this stable equilibrium point, minus 4. Very nice. Separable differential equations. We have 2 of them to solve. First, we have a particular solution. Okay, great. So we want to multiply both sides of the equation by e to the y and multiply both sides of the equation by dx. Then integrate with respect to y, integrate with respect to x. I just made another video with 6 examples of separable differential equations, so you should see it on my YouTube channel if you want more practice with these types of differential equations. But in any case, let's continue. I'm ready to integrate. The left-hand side, we have e to the y. The right-hand side, we have 6. We can add a power, divide by the higher power. Really, there's substitution here, but my inside function has derivative 1, so I just integrated. If you want to write the steps out of for substitution, perfectly fine. Okay, well, y itself will be ln of this, so we have 2x plus 1 cubed plus c. The c is inside of the natural log. That's an important part. Now, I'm not finished. We want a particular solution, which means I need to solve for my constant c. So this says that y of 0 is 0. So we have 0 would be ln of, we can solve for the c here, 2 plus c. Well, when is the natural log 0? The only time. Well, what's in here must be 1. So 2 plus c equals 1. My constant is negative 1. Here's my final answer. Y is the natural log of 2x plus 1 cubed minus 1. Next one, we have a general solution to a separable differential equation. Okay, recall that if you see y prime, that's dy dx. So we want to, let's see, divide by 2, square root of y, and then divide by x, multiply by dx. We integrate, we integrate. Now here we have a general solution. Okay, well, we're told that x is positive, which means I don't need absolute values when I integrate 1 over x. So here I have ln x plus c. Now you could rewrite this as a power. It's 1/2 times y to the minus 1/2, and then use power rule. However, if I stare at this, I see the derivative of the square root of y. So that's what I'm going to put here. Square root of y. How do I solve for y now? Well, we can just square both sides. So y is ln x plus c squared. Number 12, evaluate each integral. Always show our work. Okay, I think of A as really basic rules. although we do have this pi x on the inside. But when we go to integrate the cosine, we get positive sine. This pi will come out in front as a 1 over pi. So we have 1 over pi sine pi x. And then we add a power, divide by the higher power. And then when we integrate 2, we get 2x. Let's see, maybe I'll make this smaller so I can write my final answer a little bit nicer looking. I would write this second term as 3 over 5, so I don't leave the fraction in the denominator. Letter B, we have a definite integral. This is also not substitution. We want to break this into a sum of two terms. Okay, so we have an integral from 1 to 2. The first term, if we write this as a power, so you notice we have 5x to the minus 1 divided by x. This will be 5x to the minus 2. 5x to the minus 2. Then we put a plus. Okay, here we have 3x squared over x. This would be 3x. Now I'm ready to integrate. We write down the 5, add a power, divide by the higher power. Plus, we have 3x squared over 2. But this is definite. So I need to evaluate between 1 and 2. The thing is, this first term is really minus 5 over x. So at first, evaluate at 2. I have minus 5 over 2 plus, well, when I evaluate this at 2, we have 3 times 2, which is 6. Now we subtract off, evaluate at 1. We have minus 5 plus 3/2. Here I have minus 5/2 minus 3/2, which gives me minus 8/2, or minus 4. And then I have this part, which is plus 11. My final answer is 7. The next two involve substitution, but neither are too bad. Here, up inside the exponent is something more than just x. Also, I see a multiple of the derivative of 1 over x in my integrand. So u is 1 over x, which I can write as x to the minus 1. du is minus x to the minus 2 dx. Just to help me here, I might write this way. It's negative 1 over x squared dx. Now, at this point, look in your integral. You see, in my integral, I have 1 over 2x squared dx. So I have 1 over 2x squared dx, which will be negative 1/2 du. Negative 1/2 du. Okay, wonderful. So here is my substitution box. So I have an integral. We have e to the u times minus 1/2 du. We get minus 1/2 e to the u plus c, and then we go back to x. So minus 1/2 e to the 1 over x plus c. Here is my answer. We have another definite integral. This one's pretty short. In fact, I think it's shorter than the other one we did, but it is substitution. U is sine x, du is cosine x dx. I always change my limits of integration to u limits of integration. I find it much simpler. So when x is 0, u is the sine of 0, which is 0. When x is pi over 2, u is sine pi over 2, which is 1. Now all of this goes in my substitution box. We have an integral. Look how nice this is. From 0 to 1 of u to the 6th du. So we add a power, divide by the higher power. We evaluate between 0 and 1. We get 1/7 minus 0, which is 1 over 7. Last question. We have a midpoint Riemann sum for f of x is the square root 16 minus x squared. Now, let's go through all the steps of the Riemann sum because all of the work needs to be shown. First of all, we calculate delta x, which is b minus a over n. N is 4 here. This is 8 over 4, which is 2. Next step, we write down our partition. So start at the left endpoint, march forward by delta x until you hit the right endpoint. We see 1, 2, 3, 4 subintervals. Or if you count points in your partition, there's always one more. So there should be 5 points in our partition for n equals 4, which is what we have here. Everything looks wonderful so far. Well, next we look at what type of Riemann sum we have. So here we want midpoint. We have this extra work of calculating the midpoints. So we go halfway in between, halfway in between, halfway in between, halfway in between. These are our midpoints. Now we can jump into the Riemann sum. We have delta x times f of minus 3 plus delta x times f of minus 1 plus delta x times f of 1 plus delta x times f of 3. Well, I'll factor out a delta x from all of the terms. Now stare at your function. F of 3, well, over f of minus 3, same value, is the square root of 16 minus 9. So we have the square root of 7. F of minus 1 and f of 1 are the same. It's the square root of 15. When we add all of this up, maybe I'll just write it here, we get 26.075. All right, well, this is the end of this final exam. Thank you so much, everyone.